Lesson number 13, Guided Wave Testing. Introduction to Guided Wave Testing. Guided Wave Testing, abbreviated GW, also referred to as long-range ultrasonic testing, is an NDT method developed for detecting metal loss. Guided wave testing is a rapid screening technology. It comprises a low-frequency pulse echo system aimed at screening large volumes of materials, usually pipelines, from a single or limited number of test points. Its initial design and application was for detecting corrosion under insulation in petrochemical plant pipework, but it has found widespread use in other inspection situations. The guided wave method does not provide a direct measurement of wall thickness or the exact dimensions of discontinuities. Quantitative volumetric inspections such as conventional UT or RT are recommended after initial detection of discontinuities, particularly for engineering assessments. Advantages of guided wave testing. Inspection over long distances from a single test point is possible, giving complete volumetric coverage of the test object. Guided wave has the ability to inspect inaccessible structures, such as structures underwater, coated, insulated, or concrete encased, because of the ability to test from a single test point. It is cost-effective and time-efficient inspection technology. Equipment is portable and battery-powered. Limitations of guided wave testing. The test length or distance of pipe inspections is dependent on the exterior pipe coating, which may cause wave attenuation, type of matter, being liquid or gas, which is inside the pipe, the pipe condition, which may cause wave scatter, and the number of pipe features that reflect energy back to the transducers. Additionally, secondary NDT methods such as UT or RT are required to quantify areas reported by guided wave testing. Guided wave testing does not provide a direct measurement of wall thickness or the exact dimensions of discontinuities. Principles of guided wave testing. Guided wave testing employs low-frequency ultrasound operating just above audible frequencies, propagated from a ring of transducers which are dry-coupled around the pipe. The propagation of these guided waves is governed principally by the frequency of the wave and the material thickness. Where the wave encounters a change in pipe wall thickness, a portion of the energy is reflected back to the transducers. The distinctive high-amplitude reflection responses from welds may be used as convenient distance markers during an inspection. Guided wave is equally sensitive to metal loss on both the outside and inside surfaces of a pipe. Guided wave testing versus conventional ultrasonic testing. In conventional ultrasonic testing, the transducer must be placed directly over the area of metal loss in order to successfully detect it. Multiple scans by a longitudinal transducer would require a great deal of time and expense to thoroughly evaluate a pipeline of significant distance. Not to mention, it requires having the pipe completely exposed down to a clean surface for 100% of the inspection. Guided wave transducers transmit and receive a signal along the pipe wall. Where a pipe cross-section changes, the acoustical impedance change causes the signal to reflect back to the transducer. The aim of inspections is to rapidly test long lengths of pipe with 100% coverage of the pipe wall and to identify areas of corrosion or erosion for further evaluation using other NDT methods. Inspection ranges. The pipe surface condition, geometry, and contents all impact the inspection range. The figure here shows the performance summary of guided wave, which roughly determines inspection ranges depending on the variables and applications that may be encountered in the field. So looking at this figure under the surface condition column, we'll get the longest range if the pipe condition is of bare metal, meaning it's not coated, followed by smooth well-bonded paint, fusion-bonded epoxy, light pitting, heavy pitting, plastic coated, buried, bituminous coated, and then finally concrete coated, with our shortest range being a concrete coated pipe. Looking under the geometry column, we'll get the longest amount of scans if we have just straight length pipe sections. And then our amount of range will be reduced as we include attachments or brackets, branches, multiple bends, and flanges will reduce our range incredibly short, down to less 20 meters. Also is true with our contents. If the pipe is filled with gas, we'll get the longest range out of our scanning, followed by low viscosity liquids, then high viscosity liquids will give us our shortest range. And this is all based off the attenuation of the materials. If there's gases within the pipe, Then as the sound wave travels through the metal in the pipe, there's enough acoustical impedance where none of that sound will travel into the gas. But if we have a very high viscosity liquid, a lot of that sound that's traveling through the pipe wall will also go into the viscous fluids that are in the pipe, which will reduce our range that our sound wave will travel. It will just slowly attenuate out. Guided wave system components. Portable guided wave systems require an ultrasonic instrument linked to a personal computer to drive the software that acquires, displays, and analyzes data from reflected ultrasonic energy from a multi-transducer ring or bracelet that encircles the pipe. And that completes this lesson.